Welcome to today's webinar. Today we will show you how you can analyze a tunnel structure in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Mark Gebhardt. The presentation will be done by our colleague Juliane Stopper-Akdag. She is responsible for the product development, especially for the add-on geotechnical analysis, and she works also in the customer support team. The same is valid for Mark. He's also responsible for the development of the add-on geotechnical analysis and works also in the customer support team. And he will help answering your questions during the webinar. You can ask questions via the control panel on the right side of your screen. Press the button with the question mark, enter your question in that field, press send, and we will receive your question and we will answer you. Okay, that's for the moment all from my side. I hand over to Juliane. Juliane, it's your turn.
Okay, thank you, Andreas, for the introduction. I will present this webinar to you, but before that, I would also like to welcome you to our webinar today. Okay, then before we go to the program, I would like to have a look with you at the next slide to see the agenda for our webinar today. We will, in the first part, come to a short introduction to introduce this topic. In the second point, we will see, or we will model our first model. It will be a model in RFEM 6, which consists of members that are bedded on springs. In the point 3, we will have the tunnel lining in soil continuum. So we will use the add-on geotechnical analysis, and we will model with construction stages. We will define the construction stages, and we will analyze this model. We will check the results, speak about evaluation a bit, and also the documentation. After that, the main content is finished. We will just have a look at a last slide where I would like to give you or provide a short outlook on the features that will come next for add-on geotechnical analysis. Okay, then we will go to the next slide and start with the introduction. Here we have a first slide about types of tunnel defined by construction method. This slide just shall bring us into this topic. So we have the first method that is introduced here is the cut and cover construction. So there will be an excavation in the field, and the tunnel structure will be installed there, and then it will be closed afterwards. This method is of course typical for shallow locations in urban locations, and it is used for metro systems that lie in shallow depths. The next point are the mined constructions, where the excavation takes place entirely underground. There is no opening from the surface. There are methods used such as new Austrian tunneling method, shotcrete constructions, and so on. The support system, typically comprising shotcrete and anchors, is in this method adapted to the behavior of the ground and installed progressively, so it can adapt to the ground, to the surrounding ground. So this method is suitable for deep alignments, and it can be used if along the tunnel the ground conditions are variable. And the third point are the shear tunneling methods. It involves the fully mechanized excavation using a TBM, a tunnel boring machine. This method is economical for long uniform tunnel drives. Today we will work with these types, with TBM tunnels. So we go to the next slide. This is an introduction into the numerical modeling. For modeling tunnel constructions, we have to think about two components of the structure. So the first thing is that the structure of the tunnel itself needs to be modeled, and this can be done by bedded beams, by shells or volume elements. And the other component is the ground, and we can either use springs that very much simplify. Some ground values are used. They simplify the situation. The other solution is to use a continuum, 2D or 3D. The 2D continuum is very common for these plane strain situations for tunnels. The performance is not too high. It can be relatively fast solved, the model, and is able to have the soil structure interaction in one model, which is the advantage of using the continuum. And if further effects shall be considered, like complex situations, some 3D effects, then of course the 3D continuum is also an option and the appropriate solution. Then I have here a third point. This is for the connections. We have in the tunnel lining, we have connections. We have, if we think this is a tunnel lining here, or we can also go here. You see, we have here these contacts, and we have also these contacts, and these are modeled with contacts, with hinges, via coupling elements and rotational springs or non-linear springs. So to sum up this, for the preliminary design, embedded beams can be used, and they are supported with springs. We have here this schematic image where you can see the tunnel lining and the contact springs between the next lining and so on. It will go on, and here we see the soil springs that will be placed at the ring here. Yes, and here we see the behavior of these soil springs. So we have the normal ground spring, which is compression only. So for tension, there's no contact. It will be not provide any stiffness against tension. And the tangential ground spring, of course, goes into both directions. Yes, and for more complex situations, as we already spoke, the continuum can be used, and for the most complex situations, a 3D continuum is also appropriate. Here we can see schematic the continuum solution. Okay, then we go to the next slide. Here I've summarized some estimations. There are different options to model them, but this is about the couplings in the model of the structure. So we have here the contact between the tunnel segments in the longitudinal direction of the tunnel, and this is one example how it behaves. We have the situation that this contact starts to get closer. There's some slip here, and then step by step it's coming closer until we have a full concrete to concrete contact. So this is for these contacts. And then we have between the tunnel segments in one circle, let's say, we have here hinges. Here we can see, and this I found in the literature. This is one example how this hinge would behave and how it could be approximated or simplified approach can be used to model this. These examples are from the recommendations for the design, manufacture and installation of segmental rings from the DAUB. Okay, so we have these complex couplings, contacts and joints. Then that's it. This is what I wanted to present in the introduction. Then we can go to the model. I will open RFEM 5, and here we go. We have here our program, and I will start a new file. We will get into the base data and give our model a name. I call it tunnel 0.1, and we can give here some description. Okay, webinar 2026, and we can here switch off the solids as we don't need them in this first model. And we have here our add-ons. If we our main program provides the finite element analysis, and if we need further calculations, we have here a list of a lot of add-ons we provide, and you can just activate the add-ons you would need for your model, so the program grows with the needs of your model. But in this very first model, I just want to switch on the concrete design, and then the input, the calculations, and also the results that are needed for the concrete design will be integrated into the program. I don't need them here, and if we have a design add-on active, we also have to decide or to give the information to the program according to which standard the design shall be done. So we keep the default setting, and I just want to switch off here the representatives as I don't need them for the tunnel. Okay, then I say okay, and my model, it will be prepared, the empty model, and then we can start and arrange for us our working field. Here we have here our working window, we have here our navigator where you can see the data that you have in the model, and we have it also in the table. But let's start. The first thing I want to do is I want to modify our work plane a bit. I would like to have the grid point spacing of 0.5, and I want our grid to dynamically get its size from the model, and we need the XZ direct orientation. I would like to work like this. Okay, then I agree, and we cannot see it yet. The next thing I would like to prepare is I have an example for the guide objects for the background layers. We open here a new background layer. I prepared a small example just to show to you again that we can use them, and whenever you would find it helpful, you could add a background layer. And we go here in, and we'll take our DXF, and I want to have it to have an orientation for my tunnel to see the layer. And so we can keep here automatic, and okay, I agree. And now we can see this is my simple soil layer here, just as an example for you and also for me, because we will assign the springs, and then I can see which spring should have which stiffness. Okay, then this we have prepared, and I have one more thing I would like to prepare. We can in RFEM use global parameters. So whenever you have a model that you will use again and again, it can be quite helpful to have parameters in use, and I would like to show it to you. I will press this button here, and this is our list for the global parameters, and I have prepared a list that I want to import now here with you. And you also could save your own list. You can modify it here, you can work here. So these are the parameters I have in the model. Yeah, you will find this model in the download, and then you can check on this too, and I will translate these then. So here we have different options. We can have a definition type value. There we enter the value. So this is my diameter and this is the radius. Here I have thickness for the cross section of this tunnel lining, and here I have the odometric modulus for layer 1 and layer 2, and there's a factor for bonding. I will use factor 1, and these are the springs that I will use to represent the soil stiffness, and these spring stiffnesses, they can be calculated with these values. And we will go here and apply, and I think then this arrow doesn't exist anymore. So these are my two spring stiffnesses, and I can later use them to assign them to the supports. Yeah, and here's the one dimension, the 1 meter in the tunnel longitudinal direction, so it's 1 meter, and this is the on the circumference, the length that is considered for one segment of the tunnel lining. Okay, then that's it. So whenever you make a list with your parameters, you can also save them and import them to somewhere else. I say okay, and then I have my list here, and we can also save if the program wants us to. It's going to be saved. Then we can go as next step to the materials. Let's have a look. RFEM saves the last materials you used. So here in my case now, I don't want to have this material in my list. I want to keep this concrete. We also can get from here, well, I create a new material, then we can do it together. We have here our material library, and I want to have a reinforcing steel. I will take B500 SA and say okay, then I have it on my list here. I will check the standard. Yeah, it's fine. Okay, then that's it, what I need for my structure. Then we can go to the cross sections. I want to delete all unassigned cross sections and just create a new cross section. We have here the concrete automatically be found and provided some cross sections that are very often used, and we will use the massive rectangle, and I will have 1 meter in the width, and in the thickness we have 300, and I say okay. And here I could also assign my parameter, which is the thickness, and then it's parametric, and if I later want to calculate it with different thicknesses, I can do it and easily change it there. Okay, then we have this. We don't need thicknesses. Then now I would like to start with my modeling. I want to define the circle, and I want to place the circle in the depth of 10 meter. And it will have a radius of 3 meter, and we can do that graphically as we have the grid here, and the snapping is working very well. I do a right click, and then I can leave my last function that I did use. Okay, now I have my circle here, and from the experience in the preparation, I can say that it is useful to divide the line into 4 sections, so I need 3 intermediate nodes, and I can have these components. And then I need additional nodes because I want to assign my nodal supports there. So I have to again go to the line and say divide line at intermediate nodes, and I will have 6 intermediate nodes. It will be done for each of my segments, and this time I don't want my line to be divided, so I can use this option here, create on line nodes without dividing the line. So these are my nodes that I would like to use. Okay, I need also one help node, let's say, it's one additional node that I could use, and I also would need one that I will move into the -y direction by 1 meter. This is now here. Okay, so I have my geometry prepared. We can assign to this line, we can select it and go on the line edit, and here we can say along this line a member shall be placed, and design properties, yeah, I can have them, and we can have a look at the cross section. Here we can see that our defined cross section is assigned, and as the material is concrete, automatically the reinforcement and all the design settings here in default state are defined. You can here see the concrete cover according to standard, and for this exposure class or concrete durability we have a first preliminary shear reinforcement, we have longitudinal reinforcement that I would like to have diameter of 14. Okay, I say okay, and then I have my member here. What I need and can check right now is that they have the same orientation. We will check this. We can switch on here the local member axis, and we see that these have the Z direction showing to the outside and these here to the inside. So for this part of the lining, I would like to switch the I would like to switch the orientation so that it fits together. This we can do here in this case for the cross section. We see here now we have in this direction Z, in this direction Y, and if we rotate 180 degrees we will have the Z upwards, and it should be switched. Okay, this is fine for me. I will save, and then we can proceed with the geometry. Next step is that we assign our types for nodes, and here the nodal supports. We also can delete the not assigned nodal supports. We will have a special nodal support here now. Yes, here for this case we need the option specific direction. This helps us, or this allows us to have a radially oriented support. So I want it to be directed to node, and the first axis shall be my x-axis, and this will be the radial direction. So I need to have this node here assigned so that from the nodal releases the x direction shows into the radial to the center of the circle. And then here I will take my second help point, a node, let's say, and now I can select the nodes to that this support will be assigned, and I will use it for this upper part. So now my background layer is quite helpful because I easily can see that here above this line I am in the upper part and have the first oedometric modulus, and in the second part I have these springs for the second oedometric modulus. Okay, so now my x direction is radially oriented, and I can here define the spring constant, and I will go to global parameters and take here this CR1. And what we have is a partial, a failure if px is positive. So this one I will apply. For the other directions, I will just use a small value, and for the rotation we don't have any constraint against the rotation here for the soil. So I will agree this, and then I have my supports here. I can see them, and for me they are a little bit too big, so I reduce the display option here. Okay, and I want to also not see the reinforcement. We can see here now our tunnel lining. This is 1 meter and we have the reinforcement already placed, but I can switch it off for now. We don't need to see it. We can come to this later. Then I need to define my next nodal supports for the second soil layer. I will create a copy here, and what I need to change only is the global parameter. I can now use for the second one, and I will assign it to the nodes that are in this zone. Okay, so I do agree, and I also have here now my nodal supports. Okay, then that's it for now. We can now have a look at the layers. Not at the layers, at the loads. So we go here to loads, and in this model for now I only have the self weight. I will create a new load case, which is a permanent imposed load case, and it's the earth pressure load. Okay, I will say okay, and then it is in the list, and we can have a look at this too here. I will also do the design, a first design with you for these combinations, and yeah, these are now the load combinations that are created, and we can have here the first ordered theory, and we could also change it here in the combination wizard. Then it is generated like this. Okay, good. Then I say okay, and my load cases are prepared. Now I have to fill my load, and I would like to show you a slide again. I would like to consider the ground pressure load like this. Yeah, as written here in the tunnel lining design, this pressure acting on this ring can be simplified as a superimposed radial load composed of a uniform isotropic component and a cosinus-shaped deviatoric component. And this is from the literature. It's also from these recommendations for the design, manufacture, and installation of segmental rings literature. Okay, then we go back to our model, and for this I have prepared in an Excel file the transformation of this cosinus-shaped load into a polygon, and now I can assign the polygon load here. So here are the load cases that were prepared in the model, and I have to fill the load. What I should do also, I have now my 4 segments, and to make the next steps easier for me, I would use a member set, so I can select all the members I have and say here, not divide this time, create member set. Yeah, and then I can also use the design properties from here, and I can define it once, and it will be used for all the 4 components together. We can here go back to 8 and have the longitudinal of 4 and 14. Okay, now I have a member set, and then I can use it here directly in my member set loads. Okay, here I can assign our member set, and we have the load distribution varying for assigning polygonal loads. Here I have to change the coordinate system. I want to use the local system, and the local Z direction is the right direction. Into that the load shall be oriented. Now I can insert the Excel file where I have the load according to Dlubal and Erdmann, and this is now the polygon, and we can now see that it worked well. My polygon covers this shape of load that was recommended. Okay, then now I have one ring prepared. What I can do now is I can copy this, and I also can switch off here the local access system. I don't want to show it. Here we can switch it off, and I will show the reinforcement again. We have it here. So now what I can do is I can copy this. So I select everything because I want to have more than one circle covered. I can go here to manipulation and copy, and we can create a copy. This 1 meter step is fine, and I want 3 more rings used in my model. And then we can go here and say copy including loading. And this is fine then. And now I have my 3 rings. It's a little bit much now. We can remove the load and also switch on off the reinforcement. And I will go to the wire display. Okay, so what I need now is to define the contact between these rings, and for this I will use a special object we have. It is here, special object and rigid links. We can have a new rigid link line to line, and now I will select this first line and will assign the second line, and I have to define a line hinge, and for this I can use a diagram. Now I have my line in Y direction, so I should use here a diagram. We see here the option then to define the diagram, and it shall not be symmetric as we saw. It is only for compression, so we have a start point here like this, and then we can provide, it is just an example to show the functionality and to get close to this curve we saw on the slide. So we have here 100 and 8.7 and 600. So this is fine. This shall be now the hinge or the contact between the tunnel linings into the longitudinal direction of the tunnel. So it will be used for this here. And now these we can just copy quite easy. I would use the manipulation and rotate. And here we can create a copy, and we want 3 more copies, and it shall be placed every 90 degrees, and the y-axis shall be used. I select the center node, and now I can have here my rigid links around the first circle. And now I need to copy this again, or I can copy it to the next contacts. And yes, what we can do here to have it more easy is to switch off the member sets and the navigator display. Okay, I can select here these contacts or the rigid links, and I can say manipulation. Again, 1 meter is fine, but now I need only 2 copies. And this is how we could copy this. Yeah. then we are for now ready. Another point would be to get to place the hinges in the lining, but for today I will finish it. We can have a look at this another time. This shall be it for today. And now we can solve it and calculate load combination. For example, I can solve this quasi-permanent situation. We have here these loads for consideration of earth pressure, and we have self-weight active. We can just go on calculate. Okay, now the model is solved, and we can have a look at the results. And yeah, at first we will switch off the loads, and we can have a look at the support reactions, and what we can see is that it looks like our tangent failure worked, as we have here no support reactions, and here where compression starts we only have compression reactions. That this looks plausible. Then we can also have a look at deformations. This is the deformation that shows up. Normally deformations are also displayed like this in RFEM. If you want to see the member, you can go on section colored, and then graphics look like this. We can also here switch off this and see it. Okay, and then we can go to the member forces. And here, if we go in this view, we can see, can start with the normal force. We have the normal force, we have the shear force, and then we have the moment. And with this, the design can be done preliminary. And we can do this. We have here the concrete design. We gave the reinforcement already, so we can just start it. Of course, it then would be needed to do some fine-tuning, to go to the configurations and adapt the settings as you wish, but for first result it's possible to just do the design, and we can go to the ultimate limit state check. We can see here now that some maximum spacing of transverse reinforcement is not fulfilled. This should be looked at, but we can go on to the design ratios, and there we see that our ultimate limit state design checks, if we switch off this, are fulfilled. And we can also go here and see, if we switch off the envelope, we can see that ultimate limit state design checks are fulfilled, and you could also check the required reinforcement for these loads. So yeah, that's it for today for the model that I wanted to show in RFEM. As we already spoke about with the PowerPoint, we can say that it is a simplified approach. The soil is considered only as a spring with the stiffness calculated from the oedometric modulus, so it considers somehow some part of the soil, but yeah, it is fine for getting an impression of the inner forces in the first phase, and also to have a preliminary design and check on the reinforcement. Yeah, but if you wish and if you need to consider the soil structure interaction, then it will be needed to model the continuum, and for this we can use the geotechnical analysis add-on, and we will do this now. But before we go there, I would like to go back to the slides. So that's it for this model number 1, and let's go to the slides. Yeah, we have here this one, and we can go to the ground as continuum. So I just want to bring these 2 points on the agenda. The first thing is, if you model the continuum, this of course also has some restrictions, some boundary lines or surfaces, and you have to decide about the dimensions that this continuum shall have. And there are some provisions in the literature. I have here now this image I took from Numerical Analysis in Geotechnology from German Society for Geotechnics. They recommend, for example, the 4 times the diameter up to 5 times the diameter into both directions, and also the depth is provided. And of course this can be used as a first orientation, and you anyway should check whether these boundaries are far enough so that they don't disturb the results here around the tunnel that you are interested in. So this is one thing you should be aware of. And a next topic is the volume loss. You have, due to the construction, the excavation, and so on, you have here some material loss. And if you have here the material loss, we can imagine that the soil fills these material loss spaces, and then some settlements occur at the surface. So the material loss is quite important, as it is directly connected to the settlements at the surface and also to the risk for damages for existing structures here at the surface. Yeah, so that's why it is modeled in the continuum analysis. There are different approaches. We today will use one, and yeah, this I wanted to tell. Okay, then we can go to the model. We open RFEM 6. Yes, this is the model I want to work with you today. I have this model prepared because I want to focus today on the construction stages definition and load case definition and also results. So this time I did model it in advance. We have previous webinars that show the modeling options in RFEM 6. We have one webinar which fully is about modeling process, and in other webinars I also did model. I just can say that I did use these boreholes. We can see here I did use it to enter the soil heights, the layers that were found in these positions. I did generate the massif, and I used this surface here from the massif. This just as a short summary. Okay, then let's have a look at the model. We can at first go to the base data. We now can see that here the geotechnical analysis and the construction stages are active. So the input and options to calculate and also the results were integrated into the program, and we will have some special settings here. We will see them. Okay, first thing we will look at shortly is the materials. We have with the add-on geotechnical analysis the specific soil materials provided. So in this model today I did use the more Coulomb model. We also have the hardening soil model, the modified hardening soil model, and we have Hook-Brown model that we can offer. Yeah, and we have 2 more models in progress that will be provided, but this will come later. If you have a specific soil model, you will also have here some extra input that is required. Here we have the cohesive strength and the internal friction and dilatancy angle that more Coulomb needs. Yes, so these are my 2 soil layers. The one that is number 3 is a little bit less stiff than number 1. Okay, and here I have linear elastic copies of them, so it's the same material data, but I selected material model linear elastic. Yeah, then we can have a look at the geometry. We have here a kind of a plane strain model. It is a 3D model, but it has a very thin thickness, as we say we have plane strain conditions. And I did here the geometry is prepared, so we have here the soil, we also have the tunnel geometry and some contact solids Yes, but you will see this later. And we have here at the top some the slab of a previous building, or a building that was already placed there. I want to make it visible for us, so we can go here to the navigator for display to change settings, and let's check. Yeah, if we fill it with thickness, we can see that I have a kind of slab here, just to show that with the continuum solution, of course, you on the one hand have the full soil structure interaction in one model. So if something is changed for the tunnel, directly the soil gets the changed influence and gives adapted or changed reaction. And the same thing is that we can, of course, consider the influence of structures to each other. So that's the big advantage of using continuum model. Okay, so this is the model. Then we have here the loads, so we can go there. And as I said, I want to show one option to a kind of model kind of volume loss. So I create a new load case that I want to use for this. Yeah, we can call it line contraction, as it is modeled in this way, and we will have a look at it now. And we can see here we have these surfaces, and these surfaces, they are the concrete surfaces, and I want to now select them and make them visible. So this is my concrete surface, and to these surfaces I want to assign the load. So as I have created here the load case, I receive here folders for these loads. I have to fill them now, and here I can take the surface load and I do assign these surfaces, and now I can put the load, and what they do is you can place an extra strain. And this is in our Y direction, and for the start we take 2%, and this should be should be approved, and it should be minus. It should be tension in the shell, and we can imagine if the tension is assigned, contraction occurs, and there's some space provided where the soil moves into the direction. Yeah, so now we have the line contraction prepared. Yeah, and then we have the things that, of course, later further loads could be placed, but this shall be for today it. So we now will work with the construction stages, and we have, for construction stages, we have to define always the objects, and this is the place here where you can do it. I want to show you, we also have a geotechnical analysis folder that came with the activation of that add-on, and here you see the boreholes that were used. Okay, but that's for this. Now we go to construction stages. Okay. We see here our first construction stage, and we can here edit which objects we will have in the first stage. So the first thing is I want to add all solids, and then I will remove the ones I don't need. I don't need for now the contact solids that I have here and here. Then my solids are defined. I can now modify the surfaces. In the first step I assign all surfaces, and now I remove the ones that I don't need. What I don't need is the surfaces of the contact solids, and we remove them. We have them here And I will also remove these small surfaces. Okay, and I will remove these inner surfaces as they are the tunnel lining, and they shall not be existent in the first stage. So I remove them, and it is okay. I say apply, and now I have my objects in the model. This is my first stage, and it will be the initial state. It is used to calculate the stress state of the geometry that comes from the soil self-weight only, because we know that soil has a stress-dependent stiffness. That's why we are always interested in the correct stress state, and we calculate the stress state that exists because of the soil self-weight. And in the first step it is with linearized material model. And then we have a next stage. It follows after the first, and we will not change any objects. This will be still the initial, we call it nil phase. And here will be the non-linearity of the material activated. So, and then comes the next stage, and here we will assign the tunnel lining. So we will add these surfaces we have here. This. We will control it afterwards. I can show you. Yeah, we have them, and we will also use the contact solid. Then we have a contact between the surrounding soil and the tunnel lining. Okay, and we use the other side too. Yeah, now we are fine, I think, and we will deactivate these surfaces that are from the soil that is until now placed in the position that will be excavated, let's say. So what will happen here is excavation and tunnel lining. And we will also modify the solids. We will add these contact solids. Okay, and we will deactivate these. Okay. And then a next stage can follow. There we will not change the geometry. Here we will activate the load, the line contraction. Load. The load, the self-weight of the shell, and the line contraction we will assign. Okay, then we have finished our construction stages definition regarding the objects, and we can now go to the stages and create here the full model. And we can see now in the first stage we don't see any structure part here, and this is also valid for the second stage. And in the third stage, this is what we need to control now. The solid is removed. We have here the contact solids in use, and we have the shell of the lining in use. And for the contact solid, I need linear elastic material. That's why I did copy the surrounding soil material and used linear elastic model, as I said at the beginning here. Okay, then that's it. I before didn't show you the supports. We have here the geometry. We had a look at the mesh, and we spoke about loads, but we didn't speak about the supports. I have them. You can, here in this navigator for display, activate the types for surfaces, and there you can find the supports. So it's sliding here. Yeah, but I don't want to see it all the time, so I switch it off. Now we can go to the loads. We have to define the loads for the stages that shall be active. We go here and go to the first stage. We say in the first load case we want to have the self-weight of soil solids active, and also the self-weight can be active. The objects will come later. In the next stage we see, as they are permanent load cases, they are active during this following stages too. And here's also nothing changing, and here the line contraction will come and be active here too. Okay, I say okay, and then we also have our load here, as we can see. Yeah. Okay, then I think we are ready for the calculation. So we do start it. What we have to do too is we have to go to the analysis settings. This I wanted to do with you. We will have a look at this for the first stage. In this stage we have the soil self-weight active to get the stress state. What we don't want to have is the deformations, and this is why we have this option here active. This equilibrium for undeformed structure makes that the load case is solved, or the stage is solved, and the deformation will be reset to 0. Because we are not interested in a kind of previous deformation that happened before our construction starts. So we are interested in the stress state, but we are not interested in the previous deformations. That's why we activate this setting. Okay, and we have the same here. And in the third stage we want other static analysis settings, so I create a copy of the first one and I deactivate the equilibrium for undeformed structure. Now I want to see, as usual, the deformations, and as we have the nonlinear material models active, I will also assign load increments. I will start with 4, and this is something that can be adapted later, and I will use this new static analysis type for these. Okay, then we can start it. I say okay, and we can actually from here start the calculation. So we saw now that the initial state is calculated and some deformations, they are reset, and now the structure is applied and loaded in 4 steps. And now we also have the tunnel lining. And we are nearly ready. Here we also can check the convergence diagram more in detail. And here, let's have a look. Yeah, here we can also follow the results during the analysis. Yes, but we will receive them shortly. Okay, So this is our deformation in the fourth construction stage after application of the line contraction. And we can see here some settlements. We can also increase the display of the deformations. Yeah, we can see that here the settlement occurs during this deformation, and yeah, this can be seen here. And we can also have a look at plastic zones. Here we have criteria and we have plastic deformations, strains, and we can see some plastic strains here at the sides of the tunnel in this stage. What we can check too is the stresses. For example, the sigma 3 stresses, and this is for this stage, and I want to show you in the first stage. This is the initial stage, and here we see that we have stresses, and if we go on the deformations, they are reset, they are 0. So this helps us that we can, in this stage, and also in the first one where only the structure is assigned, we can see the deformation that happens after the initial state. So we can see the stresses, we can check the invariance where you can see it, how the flow of the stresses is working in the model, and we can of course check our tunnel lining. I actually have some result beams prepared. I can shortly activate them. I need to have them in the stage so that they are doing their job. So I will assign them here. Okay, and I will calculate the last 2 construction stages. Then we can also check the tunnel lining forces as member forces. Yeah, we can print all these views into our printout report. I will show you. I have a prepared one, and we can also send a screenshot together. We have multi-print options, so if you like a special view, you can print with this view and set which load cases, which load combinations shall be print for this view. There are a lot of settings possible, and here we go. We in a bit will have our member loads too. Okay, then we can check it. Yeah, now we have member. So we have these result beams. They integrate the stresses of objects that you did assign, and I have here my tunnel lining, which was a surface, and then I let the beam integrate this surface's stresses. You can here say which object, and I said surface number 25 shall be integrated with this member, and then I can look at the inner forces as member results. And let's check, what do we see here? It's the moment. We can also see the normal force and the shear force and the moment. Yes, and we can also create result sections. I can create a new one. I don't want the solid to be considered in this result section. I want to take this surface here, which is actually kind of simplified building, let's say, and I want to have a cut from here to here, and then we can set it active. It's now this section, and why don't I see it? Do I have some here? Okay, then you will have the option to download this model, and there the result sections will be, and you can work with them. Oh yeah, I had the wrong result. Yes, I had the solid result active, so that's why it was not working. So this is I will switch off the member results. This is the results section I did. I can activate also the description for it so that we know what we see here. Where's my setting? Result object. Yeah, this is the result section in this neighboring building, and now we can see which kind of deformations happened to that building due to the construction of the tunnel and also the volume loss. As we can see here, yeah, there are a lot of features that could be checked. We also have the invariant results, which is a solid result we see here. We have here the invariance, which is the isotropic component, and here we have the deviatoric component of the invariance. Yeah, this we do have. There are a lot of results that can be looked at, and for example, if we go to our results section, we have it active, and we can switch off the solid result and go here. For example, if there's a view I like, I will switch off this section description. If I like this view, I can easily go here on File, Print Graphics to Printout Report, and then you can see a preview and also modify it, improve it if you don't like something. For example, I don't need this panel here, and I want this panel at the outside of the graphic. We get a preview, and also I don't want to have the full height. For me, I think the height of 30% should be fine. And this is how I would like to print it. No. Yes, in this way I would like to print it, and I can save and show, and then my printout report is presented. We also have a specific webinar about printout report. There you can find further information. This is the report I had prepared. We have different views here. And what did I print recently is this image. Yeah. So here you have it, and you can also modify it. Yeah, but okay, this is, I think, for now enough. We can have a look at the images I did prepare for the results. I put images here that we also had a look at. We have the line contraction and the deformation due to it. We have deformations here in this slab, and we have deformations around the tunnel. Here we have the plastic zones, the main stress or principal stress, and the invariance, and the inner forces in the lining. I have printed, and this is we did together. Okay, yeah, then that's it, what I wanted to show to you for today, as a short introduction into first tunnel options, or first tunnel models in RFEM 6 and geotechnical analysis. We can go back to the last slide. As I said, we have also an outlook prepared. So to sum up, we today saw two options. We can work in the main program and consider the soil just with a kind of stiffness that shall represent the soil, and have spring supports for the tunnel lining. And this is we can do in RFEM 6. And if we want to model the soil advanced, if we want to have soil structure interaction, if we want to see the influence of constructions to each other, then we can use the continuum model, and for this we provide the geotechnical analysis add-on, and this is the advanced solution and the most exact, most close. So this is what we saw today. For our geotechnical analysis add-on in RFEM 6, we are working on different topics, and the next features that we will provide to you are a plane strain model type, so that we have the real plane strain, that you don't need to have this solid model. It will be provided, and we will have material models. Chem clay model is in progress, and the jointed rock model. We will provide them in the next steps. And we are also working on pile foundations that are spring supported. We have already pile foundations that can be founded in the soil solid, but we are also working on pile foundations that are spring supported. This is it. Okay, then I finish for today. I do thank you very much for your attention, and I wish you much joy with our software. Then I give the word back to you, Andreas. Thank you.
Thank you, Juliane, for your presentation. At the end of the webinar, I have additional hints for you, for example, to our online courses. There's the RFEM 6 course, it's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. And the AI masterclass course for the use of the artificial intelligence. You can get an RFEM 6 course or an Eurocode course for free when you submit your customer project, and we will publish it. Just scan the QR code here or click at the link, and you can submit your files. Then there are free online services, for example, the Dlubal community. You can ask questions there, and our support team or other community members will answer you. Then there's the GeoZone tool for the determination of wind, snow, and earthquake loads. You can determine cross-section properties on our website. You can download 3D models, for example, as a template for your project. Then you can download the free trial versions of RFEM 6, RSTARP 9, R-Wind 3, and R-Section. And they are running for 90 days. You can find more information on our website, dlubal.com, where are the recorded webinars, for example. Then you can see the knowledge base articles and so on. Okay, that should be all from my side for today. I thank you for your attention. Thanks again to Juliane for the presentation. Thanks to Mark for the help by answering the questions. I wish you a nice rest of the day. I hope we meet each other in a future webinar. See you then. Bye-bye.